you can hear me? You can see the
Yes,
slides?
I can present you first. So
Sure.
Daniel Brunner is a CNRS researcher with the Institut FEMTO ST. His interests include novel computing using quantum or nonlinear substrates with a focuses on photonic neural networks. He was received several university prizes and the Institute of Physics 2010 Royce Prize, the Institute of Physics Journal of Physics Photonics Emerging Leader 2021 Prize, as well as the CNRS Bronze Medal in 2022. He edited one book and three special issues, has presented his results more than 60 times upon invitation, has published more than 70 scientific articles, and has been awarded a prestigious ERC Consolidator grant, and is now a pilot of the French Opéra électronique project for the France 2030 initiative. So please, Daniel, you have the floor for 40 or 45 minutes.
Thank you, Yannick. It's a great honor for me to present these results, and it's a little bit bittersweet because it also shows, or it reminds me how long I'm now working on this, and how interesting the work is, and how fulfilling, but also how tricky it is. So I was asked to provide a little bit of a contrastive talk, which is well suited to what I'm doing lately. I like to challenge a little bit more the narrative in the community. But I have a lot of slides, so maybe Yannick, can you give me a hint, like 3 minutes before I'm supposed to finish, because I will for sure have to jump some slides before coming to the conclusions.
Okay.
Okay, great. Good. So I was really interested by the questions raised before because they're almost following the outline of my talk, and in particular the training question, the cost of training, the benefit of training, and moving beyond the reservoir computing scheme is, I would say, almost at the center of my research interest in the past year. So it's exactly the questions which just came up. Good. Today, I focus on computing with lasers, with spikes, and how to train. We also do a little bit or quite a bit of work in 3D integration because I think one of the big insights in the field in the past years is that the classical integration approaches simply do not reach the size that is required to challenge, you know, of course, GPUs, but in general to reach system sizes that become really, really relevant for applications. So I will start with some initial thoughts. I quite often in my talks use neuroscience and biology as a backdrop. That means I do not want to build neuromorphic computing systems. Neuromorphic is another one of these words that is a little bit misused, and there's some articles coming out about it in the last days. Neuromorphic means, for morphism, we do something like the brain, but I would say even a classical neural network is almost as far from the brain as it could be. It is simply connections and a nonlinearity. But I think biology can give us great inspiration, and it also can serve as a humbling example to realize how far we are actually away. So one of the most powerful plots I've ever seen is created by Wavinar from Stanford. He's a true neuromorph since decades, coming from the school of Carver-Mead, the founder of the field. And this is in combination with Susana from Sao Paulo in Brazil. She is essentially the Pope of scaling in neuroscientific biological systems. So what she has done is basically provide a map in how many neurons are within each mammal and in any biological brain. So she developed a method for this, and now we can essentially say this brain for this animal has so many neurons. At the same time, of course, we can measure or approximate the energy consumption. So we know the brain takes around 20 watts. It has, give or take, 86 billion neurons. And if we look at this plot here from Corbina's paper, what we see is there's a really reliable linear scaling mechanism for the number of neurons versus the energy consumption of biological brain. It goes all the way from humans down towards a fly, and these systems are really remarkably close to a linear dependency. So this is what we can achieve, or what biology achieves with sparse 3D integration networks. So, and we can now make a game, we can see how much neurons could we create in a network when we simply tip this component, this exponent of the scaling law. If we go from exponent of 1, we go to an exponent of 1.5 and we say our power budget is limited. You can't consume much more power, for example, in your cell phone. The power budget usually is your constraint, also in our CPUs and GPUs. If we now tilt this law from an exponent of 1 that we find in biology to an exponent of 1.5, then with the same 20 watts, instead of 86 billion neurons, we can create a neural network with 18 million neurons only. If we now go a little bit more aggressive, and this is not very aggressive, we go from an exponent of 1 to an exponent of 2, then with the same 20 watts, we can only build a neural network comprising 300,000 neurons. So this shows the power and the importance of scaling in computation, and in particular of neural networks, because that means we go from the human brain towards the brain of a mouse, towards the brain of a fly, simply by raising the exponent of 1 to 2. And the sad truth is that almost, I would say 99.9 hardware demonstrations, being it classical, digital, or neuromorphic, as it is right now, work with an exponent of 2. And this is the power penalty we are paying, and this is why all of AI right now is essentially predicted to consume 20% of the global electricity within 2045, I think. So this is the core of the challenge, and this is the task we should address. The big motivation is always given that the structure of a neural network, we see here topology, we've seen this in the great talk before also, is a densely connected system of nonlinear units. If we now transfer this into a digital computing platform, then the problem is we have this almost, long-standing and never-changing separation between transformations, operations, and memory. The problem is these systems are so big that you cannot store all the weights or all the connection strengths close to the operation. You need external memory. And the problem is that this external memory loading into the computing system requires a lot of energy, and is referred to generally as the von Neumann bottleneck. The real scale of this problem can be seen here. If we just do a floating point operation, that per se usually is a linear, or referring to linear operations, we need around 100 femtojoule. If we go communicating off the chip, i.e. to an external high-speed RAM, then we need 1 to 20 picojoule. And this is really where we burn all the energy. And ideally, many of these operations could even be implemented passively at attojoule energy costs. The general view is that we can get around of this challenge using a concept called in-memory computing. In in-memory computing, the neural network really is implemented usually as a true physical mirror image of the neural network computing concept, i.e. neurons here could, for example, be nonlinear units, but especially all of these connections are realized, for example, in this electronic circuit, using something that is referred to a resistive crossbar array. And then simply using the accumulation of currents when applying voltages at these inputs, and using the accumulation of currents at the outputs, the resistors or their conductance represents these weights. And now you get rid of this shuffling of memory from external RAM into the processor. So that's mostly the approach that we're trying to implement. However, this is all good on paper. In reality, this becomes much, much more challenging, and I will say a few words on this specifically for optics, but also for electronics at the end. Another important backdrop for my research, again, comes from biology, and it compares two different metrics. The first is the speed of the human brain. So if we look at the atomistic units in the human brain, let's call them the neurons, we see they work on time scales on a millisecond range, give or take 10 milliseconds between a spike. And then we can compare this to the fastest reaction time, the response times humans can achieve, and these are around 250 milliseconds for identifying if a picture includes a human or another subject or another object. And apparently evolution has really made us efficient and fast for doing this. I guess it's because you want to know if there's a tiger somewhere in the, in front of you, or if this is the friend of your community, and you don't have anything to fear. So this shows that between these two, there's only maybe give or take 1 order of magnitude difference, i.e. the response times of individual units versus the response time of the full system. And we can show that this corresponds to only the propagation delay, let's say from your optic nerve towards the different processing areas within your neocortex, and then all the way down propagating the fingertip from the brain to the fingertip until the human test subject presses a button. Similar things can be said about the energy efficiency. Do not really worry too much about these graphs. What it essentially says that within the neocortex, 90% are used for spiking and signaling, and only very, very few things for any other transforms that or any other processes that we do not assign to information processing. So this includes really everything: learning, keeping the system, the body alive, recycling, all of these kind of different byproducts of the reactions. So it is incredibly efficient. Now we can compare this to our current hardware. The timescale of a single transistor switching its gate is 10 picosecond or even faster. So single transistors achieve terahertz scales. So this comparison of optics versus electronics in terms of speed is very delicate because we always need to specify we're talking about a system level, not a component level. At least as long as we don't reach femtosecond or attosecond timescales. However, the inference time of using a classical GPU, for example, for using a neural network is only 1 millisecond. So there's orders and orders and orders of discrepancy between response time of the component versus response time of the system. And exactly the same is for the energy efficiency. Switching a transistor gate, again, uses around 10 attojoule. But the energy of a floating point operation is 1 picojoule. So that means somewhere in between there, and you cannot just accumulate several transistors in order to get to a certain bit resolution. No, you have to do many, many, many other things which are not inherent to the energy efficient principal device. And this is again where we burn a lot of energy. A comparison, for example, if you just want to multiply two numbers, you can do this analog with a very simple scheme as seen here, or you can try to do this digitally, where you have many, many different gates, all with half adders, full adder, all combined. This here requires around tens to hundreds transistors. This here reaches quickly 1,000 to 10,000 transistors. And essentially, this is what we are doing. So these are a little bit the two worlds that we are going back and forth from digital classical computing hardware, analog computing hardware. So finally, why is analog and all these systems we're talking about essentially analog, especially in optics? Why is analog helpful and can potentially offer something for the future? So here I want to cite some of our work for the first time. The question first is, can we actually build neural networks with analog units? So analog units are noisy. And the question is now, what happens if we have layers of numerous of these analog noisy units, and then we even cascade them from one to each other? Does all of this noise build up? Do they add constructively, destructively? Does the noise level essentially remain constant across the network? At the output, can we achieve situations where we have complete quiet or a completely noised signal? So we did some very analytical, theoretical work. So here you always see the lines. These are essentially the analytical model of our deep neural network, which is nonlinear and trained for a certain task, whereas the data points are numeric calculations. And here, just using this connection statistics between the neural network and those you can easily get from a model, as well as the noise properties of individual neurons, we can now perfectly predict for an engineer, you want a neural network with a certain signal-to-noise ratio at your output, this kind of neuron properties you need. The other big message here is we derived in this paper something we could refer to as a noise operator. And it is a bit like in error backpropagation, recursively defined. The noise in layer n, i.e. closer to the output, depends on the layer before, layer n-1. So S is the noise operator. And what you can see here for certain different parameters, and these tune the nonlinearity in our neural network, we can see that essentially all of these noise operators reach the diagonal. And as soon as they reach the diagonal, noise does not increase anymore if you make your neural network deeper. So what that means, even for bad neural networks, your noise or your signal-to-noise ratio does not collapse, or your noise at the output does not diverge. More interestingly, here, these are all for strongly nonlinear system. If we go to a neural network that per layer, and that's the importance, per layer is weakly nonlinear, actually noise can be averaged out and completely suppressed unless you have correlated noise. So if you're more interested in this justification, you can down here look at this reference. So this gives us more or less a justification. Why is it a good idea to build neural network, or why is it possible to build neural networks using analog hardware? I mean, one might say, you might not be surprised, the brain makes it work as well, but the brain is very advanced, and this is just using simple nonlinear units. So the justification to switch from digital to analog lies within this very fundamental scaling between the two concepts, where we can relate precision and energy consumption. So these are in unit of kT, so let's say the atomistic energy consumption unit. And this again is another paper by Wavinar in 2017. We can look at here precision. Forget what neuromorphic means. Let's just compare analog, and this is digital for different technology nodes, so 19 nanometer or 28 nanometer. So you can see this already back in the past a bit. But we see that for low precision, we have orders and orders of magnitude energy advantage between an analog and a digital encoding scheme. It is only later for high precision calculations the digital takes over. And these precision values are actually quite easily achievable in our analog hardware laboratories. So it's quite okay to achieve 6 or 8-bit precision with your optical systems. 10-bit becomes a bit more struggling. And for this, we can expect 4 to 5 orders of magnitude more energy efficient encoding than if we compare this to a digital scheme. So these two slides I wanted to include because then we can really justify, because essentially this now links to my previous slide, that we show that we do not need excessive precision in neural networks because the noise is averaging out and it is always bound. It does not diverge. So this basically is the chain of argument. First of all, we do not need high precision. Noise in this case represents precision. And lower precision justifies analog computing by orders of magnitude less energy consumption. And these kind of energy scaling laws, we are not so far away. Just using a laser and a photodetector, you get within order of magnitude of these energy consumptions per bit of precision. So now I go to the autonomous computing with lasers. The system we're really, what I always say, using in a couple of past years is a classical optical laser, semiconductor laser structure called a VCSEL, a vertical cavity surface emitting laser. They can be everywhere. You can buy them literally for €5 from Amazon or whatever online delivery system. Why do we dare to call those a layer of a neural network? So a VCSEL has this structure. At the bottom you have a mirror, at the top you have a mirror, like in most lasers, and in the middle you have an optical amplification medium. So first of all, why is this a network? If you have a small VCSEL, you have a single mode emission. That clearly is not a network, or you can say it's a three-dimensional network because you have phase, amplitude, and carrier inversion as the three variables. However, if you increase the diameter, then of course you get a multi-mode system. You get a lot of modes. And then these modes can interact because interaction mediated either by carriers or by photons. So local interaction is mediated by the carriers because inside of the quantum well here, for example, you have diffusion processes and they interact with their neighbors within a range of, let's say, give or take 10 microns. You get a global coupling because as a photon is emitted, let's say at this position within my cavity, the original size of the wave package is more or less given by the NA of the largest NA of the VCSEL. But then, so that would say a couple of micrometer in size. But then as it bounces through the resonator, during its photon lifetime, diffraction leads to spread of that wave function. And this goes to around 100 micrometer diameter within the couple of picosecond lifetime within the cavity. So that creates a global coupling. So the second ingredient we need besides coupling is the nonlinearity, and semiconductor lasers are full of them. Lasing threshold, a phase amplitude coupling similar to the carrier effect, but it's on much slower timescales and gain saturation. So this is why we dare to do this kind of analogy that a non-optimized large area multimode VCSEL is similar to a reservoir as we have seen it in the previous state. So how do we information process with these devices? Here you see the laser without any optical input, just electrically biased above threshold. Now we inject a multimode field. This could, for example, be a scenery, an image, a pedestrian walking across the camera of a car, or it's not a camera, in this case the laser, but the pedestrian walking is injected into the laser. If we do off-resonant injection, you see nothing is happening. It's just a simple two fields, the intensities are superimposed and square, and there's no real interaction. I.e., we don't have a nonlinear transformation, we do not really have a reservoir. If we now put the two on resonance, this changes drastically. We have this self-organization, we have a very sensitive behavior of the modal distribution versus the particularities of our input, and we get these kind of nonlinear Turing patterns in the laser's near field. So this corresponds to a dimensionality increase of the injected information. This is exactly the effect we then leverage for computing. So to build this system, I have purposely removed here reservoir and call it now an RNN, because we now, since a couple of years, are beyond reservoir computing in my team. We take an input information, that is the image on a DMD, for example, a handwritten digit. From there, we inject it into our recurrent neural network. It's still recurrent because, you still have these intra-layer connections within the reservoir that I just introduced, according to an injection matrix. Then we have the nonlinearity and the transformation in the reservoir or in the RNN, in the recurrent layer. Then we have our readout weights to project it onto the output. For example, for handwritten digit input, if this input image is a 5, then output number 6 should have the highest intensity. How we do this in the experiment is we have an injection laser that is tuned to the wavelength of the VCSEL. Our input information is displayed on a DMD, that's just a spatial light modulator with mirrors, so it's much faster than SLM, which is why we use it for the input information. The input weights are represented by a multiplication of another spatial light modulator, phase or amplitude modulation, and we propagate our signal through a multimode fiber, which adds another random connectivity on top of it. So here, experiment versus the scheme, input information and SLM and omega in are switched in order. But since we do a pixel by pixel multiplication, the sequence doesn't really matter. It was just easy in the experiment to implement like this. The near field output here, we now image on top of the VCSEL, i.e. we inject it into our VCSEL. The reaction of this laser to the particular input image is then imaged again on another spatial light modulator, or in this case, the same spatial light modulator, which is then applying the output weights before we detect it. So this means in the system, all information processing is happening physically by wave propagation, by diffraction, by nonlinear transformation due to the laser rate equations. And there is no digital or classical pre or post processing going on any longer. There is only sending information in and getting optical power at the output. Everything is done physically. We could run this entire experiment controlled by a very simple FPGA or Raspberry Pi, and this is actually something we are trying to do right now. So that's our physical system and I will use that one to explain different concepts now to train the neural network. So for example, you might reformulate it, and what I am interested in lately is data-driven programming of analog computers, because ultimately our neural network is an analog computer, and I do want data-driven, not premeditated programming. So for this, I like to use this comparison. On the left side, we have more or less how we humans are learning. On the right side, we see what is done currently in machine learning. So here we have a kid learning how to play tennis, and we have a teacher next to it. And there's some interesting details about how this goes about. So the teacher gives very high-level feedback to the girl learning how to play tennis, and the teacher is completely agnostic about the neuronal state of the girl, about the topology of the neural network, anything. So the teacher does not know anything about the kid playing tennis besides where the ball goes and where he said the ball should go. And the same is even true about the girl. The girl doesn't know anything about its brain activity, topology, etc. It just explores different configurations and tries to find out where did I do better, and tries to identify the systematic relation between modification and improvement in response. Deep learning is almost orthogonal to this. In deep learning, in the error backpropagation algorithm, you need to know everything, and I mean absolutely everything. The connections of the network, you need to know the activity of each neuron for each example of the input, you need to know the derivative of this, and you need to basically calculate transposes of matrices as well. So it's completely contrary, these two different ideas. So we are in my team focusing on this kind of approach where we use evolutionary and reinforcement learning strategies as well as measured gradient estimation, and both of them I will split. So the first evolutionary kind of algorithms, they all more or less follow a scheme like this. Here we see our performance landscape. Yellow means good, red means bad. And now we want to shift the system from a bad initialized point towards the optimum. How can we do this? Every blue data point here corresponds to a trial at a certain stage before we change the configuration of the network. So for example, in our laser, this would mean every blue dot here is different images put on the spatial light modulator corresponding to the weights. And then for this, for each image, we push a couple of hundred or 1,000 examples of the handwritten digits through the system and measure the error. Then we have collected this data on the cloud, and then we create a next generation of this SLM weight cloud, for each of which we then have to push our data through the system again. So the easiest would just be you evaluate the performance of random distributions of your weights. Then you take the best result, you make this the average of your next distribution, and you repeat this and repeat this and repeat this. This is how this illustration basically goes about. But of course, there's better methods, reinforcement like policy gradients, etc., genetic algorithms. Ultimately, they all work like this. And the big advantage is they are model-free. I don't need to assume anything about my device. I wiggle my system. I try to correlate how performance behaves as I wiggle in certain directions, and then I go forward. So the first way we've implemented this is with discrete weights, where we use the DMD also at the output. So trinary weights, -1, 0, and +1. The problem is with this, you cannot really use these kind of analog wiggling schemes because it's too discrete. So we updated something called a simulated annealing algorithm. I will not go really down into the details. You can have a look at this publication from this year. We updated the simulated annealing. Essentially what happens is that here we only trained readout weights that are trinary. And at each stage of the optimization, we invert a certain number of weights. And then we see if this inversion was good or bad. If it was good, then we keep this inversion. If it was bad, we do not. And the question is now, how many of these weights do we wiggle? And this corresponds to an annealing schedule. Is basically the temperature of simulated annealing. It's basically inspired by metallurgy. And what we introduced is that the number of mirrors we are wiggling at each optimization epoch is proportional to our error. That means at the beginning, we wiggle many. At the end, we wiggle very few. And the cool thing is here that it improves the performance of simulated annealing a lot, and it uses dramatically the number of hyperparameters you need to scan. So here is our scheme. There is some more thermoadaptive simulated annealing scheme with many more hyperparameters, and we achieve the same performance quicker with less hyperparameters. So we've implemented this in our system, and here you can now see the performance for this MNIST classification digit task. Digital linear is, for us, I would define the gold standard as, or not the gold standard, but it's the criticality threshold. As long as we are not better than a digital system, we are not justified to introduce our energy-consuming lasers. So this here, of course, is computed with computer, so it has full precision, etc., etc. But yeah, it is a little bit the threshold we place ourselves. So this is given for all the different digits in the green bar. With our trinary weights and our simulated annealing algorithm, we do start to get close. And I would like to stress again here, there is no post-processing going on whatsoever. But we never beat it. For not a single class, we surpassed the linear threshold limit. So now we replaced the trinary readout DMD with a 10-bit SLM, ultimately we only have 8 to 9 bit because of the 2 pi periodicity or the pi periodicity. But anyway, we now use this also to start dimensionality analysis of our laser, because the question is, how many neurons does our laser provide us? What we do for that is we first only look at the readout weights. Our input weights are not yet optimized with one of these black box optimization concepts. And then what we do is we group many pixels together to one pixel. And this is essentially the data down here. And then we train the system. And with this, we only get to around 80% classification accuracy. And then we make these superpixels smaller and smaller, i.e. we give more and more trainable dimensionality to the system, and we study the impact on performance of this. And you can see always for not optimizing the input weights, and up here is the linear limit, this dashed line, and you can see if we only train the system as a reservoir, because here we're not optimizing the internal or the input weights, we never really beat this linear limit. We had one laser that was much better than this one. Unfortunately, it died after we trained it, so we don't have so representative data for this. With that beautiful laser, we were able to surpass this linear limit, also only training the output. However, as soon as we start training the input and the internal connections, we see a big difference. So here we now clamp our output dimensionality at 2500. So this is remarkable for two things. Well, or for one thing. Our single device that has not been edged, structured in any way, it's a laser that costs you 5 euros, maybe 100 euros. It can react at 20 gigahertz scale. It has up to 60-70% wall plug efficiency. It provides at a couple of milliwatt energy consumption already thousands of neurons in this case. So this is really promising, and it shows that if we use hardware a little bit more creative in this direction, we actually can really become competitive compared to digital computing paradigms. But there's many other caveats to this story. Now we start training the input, and again we do the same trick with scanning the input parameters and the parameters of input and recurrent layer training. And we see a strong increase of performance starting from this 85, 86 threshold without any input training, reaching now 91, significantly surpassing this linear threshold. Again, for our most beautiful device, we reached here 96.5% actually test accuracy for the MNIST, again without pre and post processing. And as far as I'm aware, for a fully analog system, this is the record so far ever achieved using electronic optic whatsoever. Now here a little, I'm almost begging for this. This was the work of a really outstanding PhD student, and we somehow missed the time to publish all of these beautiful results or submitted them because we're working on far advanced, more advanced things right now, or we go into a different direction. So all of this work is in this archive paper. It's almost 20 pages long because it's 2 chapters of the PhD thesis, and we will not submit this. So please, if you are interested in this, cite the archive paper. Don't wait for another higher impact publication. We will not submit this. This is where it will remain. It includes all the algorithms, etc. It's a beautiful work to read. If I may say, I'm trying to give kudos to my PhD student, previous PhD student Anna Scully here. So this is where we at. Now, in a really interesting collaboration with the team in Poland, which is creating non-circular VCSELs, we have now started to investigate the interaction of this dimensionality versus the performance of our neural network. And for the first time, we can now plot a scaling law, again on a double log scale, of the computing error versus the number of principal components. So I don't have time to go into detail here into this. We use principal component analysis as a model agnostic kind of measurement of the system's dimensionality, i.e. number of neurons to determine how big is our neural network. And we can start to see a clear carving out of the scaling law between performance and dimensionality of the neural network. So this is like the scaling law of analog computing in our systems. And I'm really happy that this work is strongly continuing. And here we are starting now, we're making first steps to link this actually to fundamental laser properties what we plot here is the number of modes versus the wavelength of the VCSEL. And then we determine this dimensionality, the number of neurons versus the wavelength of our injection laser. So we can see a clear correlation with the local mode density, if you divide this number of modes by the integration window, between the number of modes as well as the size of the neural network we are able to realize in the system. So this will most likely be published in 2026. And what is so crucial and important about this is that this now gives us a path towards optimizing, for example, shapes of these VCSELs, do more fundamental studies. Where does this dimensionality come from? Where is the nonlinear science behind this? And essentially here we are now first time linking, first of all, the importance of these dimensions for computing. Second of all, the origin of these dimensions with the physical system standing behind it. Good. Finally, I will very quickly now, because I want to go to the training a little bit more, talk about how to compute with spikes and what excites me personally about spikes. We have created a testbed system where we have an SLM being imaged pixel by pixel onto a camera. The spatial light modulator is then driven by input information like a reservoir computing scheme. So we have input information U, random injection matrix, omega inject, some scaling component, etc., etc. We add this to a bias. On the SLM is imaged onto a camera, and this forms a loop. So this creates this kind of recurrent state equation we have here for the classical reservoir computer. Now, of course, many people have done this. We have used a system like this since 2017. Also in Metz, Damien Rontani has done really interesting work with this kind of system. And you rightfully say, this system is not excitable. This cannot create spikes. True. So what we have added to this is we have added a high-pass filtered component, i.e. a sliding window integrator that feeds back negative into that system's argument. So, and what happens here is now we can look at the stability diagram. So let's say we sit our system here at this point, choosing bias offset here. So that's the rest point of the system without any input. We now drive the system with an input here, and we see here this the fixed point of the system, stable fixed point, unstable fixed point. As soon as this drive crosses unstable fixed point here, the system gets projected towards the upper stable fixed point, and this would normally be by stability, because then the system would just do its stuff around the attraction basin of point C. And this is now where this negative low-pass feedback forcing comes in here. As long as we're down here, that term is really small, and the system is just shifted a little bit. However, as soon as we become big in amplitude, that integratory term explodes, and since it has a negative feedback, that means up here that term explodes and starts to force our system back down here. So that means without input, we rest here. The system will relax back to this point if we do not cross post unstable fixed point B by the external drive, i.e. that creates the criticality you need for excitability, but then you need to be brought back to that rest point, and this we achieve by this negative feedback. So with this, we have implemented, admittedly, a very slow spiking optical neural network. However, we have 40,000 neurons, and we can now inject that with, for example, MNIST digit data. And you see these are the spike trains that are created by this optical system as a response to digit 2, 8, and 1. All good. Why do we want to do this? And this is a question always is answered very easily. Why, or people answer this very ad hoc. Why is spiking nice? People say energy efficiency, people say robustness to noise, but the details of these arguments are very, very tricky. It is very difficult to show that the spiking system is more energy efficient or more robust to noise if you cannot link it to an information encoding scheme. The power of this information encoding scheme I will now show here. That's from a paper of Simon Thorpe. He's now retired. He was a theoretical, or is a theoretical neuroscientist at the CERCO Institute in Toulouse, CNRS researcher. So here we see a numerical, a computational spiking neural network. And what you can do is you let only a certain fraction of neurons spike. Yeah. So what you see here is if we only allow 0.1% of the neurons spike and we reconstruct the information of the input using convolutional operations, then we already start to see some structure of the input image. If we now increase this to 0.2%, it's almost completely identifiable as, you will see, a bridge. Yeah? And this shows that you can use spiking neurons for very, very aggressive information compression. What this scheme uses and information encoding is not the spike rate, but it uses the delay between input stimulus and the neuron spiking time. And this is called spike latency encoding. And as you can see here, for different images, neurons correspond, because the image is always injected at this kind of step here, neurons respond to a very different delay. Now we can implement a very efficient scheme. We can say, okay, we inject our information, and now we wait a certain number of time steps, and only in this window we allow neurons to spike. After that window, we switch off the power supply, and this allows us to save a lot of energy. Importantly, this is only one global control variable. Again, we don't care at all about what the individual neurons do. We only control the length of the time window after a stimulus for which we allow neurons to respond to that stimulus. And here, for example, this is what happens if we only allow one window, one integer time step here, then only 1.02% of all neurons are spiking. If we allow all of them, then on average 81% of the neurons are spiking. And this is controlled, this ratio is controlled by a single parameter. So we've implemented this system, and we have now trained, again, the output weights of that system using another algorithm, which is called SPSA. I will not go much into detail here. It does not work on a large population of these different configurations of the weights, i.e. our SLMs. It only repeats these measurements twice. Once for a random negative perturbation on the weights, and once for the same random but positive perturbation of the weight. And with this, you get a stochastic approximation of the gradient, and then you simply do gradient descent on the weights. So that's a very low complexity training algorithm, and hence the name simultaneous perturbation stochastic approximation. So we use that to train the spiking system. And the fascinating results you can now see here is we plot sparsity as the x-axis, and we plot performance for training and testing on the y-axis. So you can see here that the performance in robustness is, the performance versus sparsity is very robust. Actually, sparsity is beneficial, and that's backed up by theory. That means the least, or the less neurons we allow to spike, the better the neural network gets. And this is because patterns become more exclusive. It's harder to find a pattern where only 5% of the cells are supposed to be active than when 50% of the cells are supposed to be active. So that's more or less the hand-wavy argument behind this. So besides this, what we can also see is that the drop here is actually quite forgiving. So that means we can go until 90% sparsity and still achieve close to 80% accuracy for solving this symbol recognition task. We can go even further. We go to close to 2% sparsity, and we are still at 60% accuracy. And this is now very important because you can tune the properties of the system with a single global variable. For example, flight or fight responses. For example, if a robot needs to react very quickly to a critical situation, i.e. I fall down the stairs, then you want to be very quick and very efficient. So you make this reply very short-lived only. But if the robot should, for example, contemplate, should I do this rather complicated action, then you give it a little bit more time to basically reflect upon this decision. And you can do this nice tuning now between efficiency and speed of response with a single kind of tuning knob. So this is for me where one of the big powers of spiking systems work. Okay, now to wrap this up, I'm coming to the cost of training an analog system.
You have 3 minutes, Daniel. As you
Good, perfect. So there's 2 approaches right now in the field. We can use this approach called physics-aware training in a great paper by Logan Wright, Peter McMahon, et al. In 2022 in Nature. And they create a digital twin which they train or optimize in order to mimic the physical system. And then they pass the data through the physical system, but also through the digital twin replicating the dynamics of the physical system. But when they want to update their weights, they only use the now differentiable digital twin in the backward direction. And with this, you can essentially force the error backprop mechanism to be implemented in a physical system. And what we are doing is we are trying to optimize the black box, and we are treating it as such. So, and here I can only show you so far our analysis of this cost using black box optimization in a collaboration now together with Peter. We are also extending this to their physical twin model. And this is not yet published results. What I want to show you here is that, first of all, number of parameters versus accuracy. I showed you before. It also then depends a lot on the training algorithm. This is again for our lasers. SPSA, this vary only 2 iterations per epoch versus different kind of black box population-based algorithms. So now what we did is for different sizes of this neural network, we measured how much memory do we actually consume in order to train our system. And we plotted this as a number of parameters. And you can clearly see that there is this orders of magnitude scaling difference between them as memory budget for best accuracy, i.e. to convergent in gigabyte. So first you can see that this makes a large difference, but this does not tell the full story because it does not link it to accuracy. So linking it to accuracy you can see in this plot. So to train our laser neural network using SPSA, we can actually go to almost below a megabyte for the smallest neural networks. So it's very, very, very efficient. However, if we go bigger, we need a couple of tens, 100 megabyte maybe, but performance remains very mediocre. And now we have 2 different of these population-based algorithms to compare, and we can clearly see both of them reach the same performance, and the one we actually thought would perform best in terms of accuracy is this one. However, you can see we go from essentially gigabyte costs of training it to terabyte costs. So there you see this gigantic interaction in terms of, first of all, benefit of training the full system, because in performance, because SPSA cannot leverage the input weights or the internal weights, it's just too crude for that. But also the charge you place on your algorithm and on your hardware outside of this. And this places a little bit at jeopardy this entire concept of building efficient neural networks if we do not solve the problem of training them efficiently as well. Good. So some final thoughts. I do not need to talk about integration. I think that's clear. I skip that. The final thought I want to communicate here is what is done a lot in the field is we create very small model systems and then we extrapolate because we need neural networks comprising thousands or millions of elements, and we just extrapolate a linear scaling, let's say, between those. The reality, unfortunately, many times is different. It is like this. And this is actually very powerfully demonstrated by this breakthrough paper in Nature Photonics 2018, I think, where they calculated, and then the startup coming out of this, they created this really absolutely amazing hardware. It's a PCI system. You can program it with Python, and you can implement a large language model on this system. So I admire this work. I'm not trying to disqualify this work, but they come to the same conclusion. Funny little detail is someone screwed up the PCB design. So here you can see a hand-soldered wire. But what the extrapolation of their original paper was 10 to the minus 6 picojoule per floating point operation. Where they end up with is 1.2 picojoule. And that's exactly the same as the NVIDIA system. And I do not have time to show the scaling arguments leading to this. The problem is these scaling arguments are the worst for the time delay multiplexing, because then you need actually this external memory for every little way to implement. So that's basically the summary of this. And if you're interested in kind of a real world contrastion of how difficult it is to beat NVIDIA at the game or digital computers at the game, I recommend to you this article by a pioneer of optical computing. I think it's from 2012 or 2015, where he already says, 30 years ago, this was what I knew for a fact. Electronics reaches natural limits. Optics alone can offer massive parallelism. I was all wrong. because computing is much more difficult, as you can see in this image. The actual optical unit is very small. The rest around it is scheduling, trying to make it reproducible, trying to control it, interfacing, etc., etc. And this is where the energy is burned. Unfortunately, not here. This will only start to save energy if we make the optical analog in-memory computing unit much, much bigger. And with this, I really thank you for your attention. And it was an honor for me to present our results and what we have done in the past. And I'm happy to take any of your questions.